Okay, so last time we talked about modal logic and also constructing possible worlds as well as the primary model we're working with, which is basically the structure and C and some R. Or an M is a set of all possible number sets maybe, or it's basically what worlds we're going to be using in our studies. So an example of that would be in person theory. We're in one world is accessible, another. We're talking about different types of sort of vector spaces. So if I have one vector space that follows this law of linear combination, where we can break up a position vector into a linear combination of the basis vectors. I will call this 1 plus beta 2. Then if we have another world that falls under this model, of course, they would have to also follow this structure or this defining feature. And then the first world, which is the base for this rule, or where this rule came from, it carries on, or this rule carries on to other possible worlds under this model. And another example, of course, is spaces. So if we think of M as a set of a lot of spaces, or maybe all spaces, maybe M spaces or P spaces, as such, or something like that. One space is another, or there's a relation, or a relation function between, or accessibility function is made possible via the function that we associate between these spaces, which is homeomorphism. Now for groups, maybe homomorphism is going to be our function here, and the relations, of course, we can get from one group to another via this homomorphism. Okay. Okay, so that was the last lecture. So this lecture we will construct the naturals. Okay. Now the thing with number sets is that, right, you can say, well, I just have the naturals. I just have n. But that's not enough, because you guys know that natural numbers can be added, can be subtracted. Each natural number has a successor, or a number that precedes it, right? But just saying that n exists, right, or n is a thing, is not enough for us to reinforce our intuition when it comes to these numbers. So really, when we construct n, we don't just say exist, but we are trying to make its structure, or we're trying to define its structure. And so really what we're doing is constructing n, or this structure, and with addition and a special operator s, which is the successor function. So yeah, of course the addition operator is a binary operator that takes n, or inputs from n, and then outputs another natural number. So we will also show through that n itself is a groupoid, or a monoid. And this s function here is a unary operator that takes n and gives us another natural number. Okay, so where do we start? To construct the naturals, we need to lay down some axioms, which are the defining rules of what exactly our structure is. So, all right, I'm just gonna put it here at the top of the board, what we're trying to accomplish. And so we're trying to construct this structure. I mean, you can express it as a triplet, or an ordered triplet pair, or ordered triplet, but I will use angle bracket notation for this type of thing. Okay, so our goal is to make this. So where do we begin? let's begin with the Peano axiom. So what's the first axiom that we want to establish when it comes to natural numbers? Well, mathematicians can argue that 0 is part of the set, or is an element of the natural, so it's also a natural number. Because mostly if you do the inverse operation between two elements of them that are the same, we should get some identity element with respect to the addition operator. So it's required somewhat that 0 is part of n. So that's our first axiom.
0 is part of the natural number.
Yes, sir. So our first axiom is that 0 is the element of n.
Because you were expecting
Okay, so that's the first one. That we need an additive identity, or we need some elements such that when we do the inverse operation of the addition operator, which is basically subtraction, we need something that gives us, or we need an element that is part of the set that makes the structure closed and thus a meaningful structure. Because meaningful structures must be structures that are close. Okay, so the first one, 0 is part of the natural numbers. Now, the second axiom is that for all x inside the natural, so all natural numbers, it must hold that x is equal to itself. Of course, we can't have a natural number, we can't have two natural numbers who are exactly the same but distinct, right? We need this property so that when we claim that one, let's say 1 is equal to 2, that's not true, right? We need that. We need to establish that every element in this set is distinct. And so that is encompassed in this axiom, that every distinct element of the naturals equals itself or themselves. And they cannot equal any other y. And a corollary of this axiom is that if two elements are equal, then y is just x. So if we claim that x and y are distinct elements, and then we establish an equivalence relation, an exact equivalence relation between these two, it must be that y is just precisely x in order for this to hold true. Because intuitively speaking, it cannot be that 1 equals 2, because they are two distinct symbols of two distinct objects. So yeah.
Am I right? Algebra topology is about abstract math.
Yes. Your master. So that's our second axiom. Our third axiom is what I said over here. It's a corollary of the second axiom. The third axiom states that for all two elements x, y, natural numbers of course, y equals x implies x equals y. Or it cannot be that x is equal to y if y is not equal to x. So we are establishing the commutativity of this equivalence relation that we have established that, to be defined, well defined over this structure. So if one element is equal to another element, it must be that that other element is equal to this first element. Okay, and then also it rings true with our notion of uniqueness, or uniqueness of each element in N. So that's the third one. So, alright, the fourth one establishes our notion of associativity, or transitivity, I mean, not associativity, but transitivity. And it states that for all three elements, x, y, z, in the naturals, y is equal to x, and x is equal to z, then y is equal to z. So, if I want to solve, let's say we abstract the numbers into, into variables, and then I want to solve for a variable, say in a system of equation, we need this notion to ring true, because we can solve systems of equations made from natural numbers, or abstracted from natural numbers, if this axiom doesn't hold true. Because if this axiom is not true, then that means that I cannot say substitute, or I cannot use the substitution rule in solving systems of equations anymore. Because it's not true that these variables transfer from one to another. Okay. So this axiom allows us to solve equations of more than one variable, or more than one unknown variable. Okay, so the fifth one, the fifth axiom. The fifth one is that for all two elements A and B, and for all two symbols A and B, and B is an element of naturals. Now we don't know just yet that A is part of the naturals. All we know is B is part of the naturals. And we're quantifying over all values of A. Okay, A is equal to, or is in, A is in N, if and only if A is equal to B. So any variable or any number or object that we know that we don't know to be a natural is only a natural number or object if for some other natural number they are both equal or one and the same. Okay? So yeah. Okay, so this is where our successor function comes into play in the sixth axiom. I'll just list them above here. These are all called the Peano Axioms. The Peano Axioms. The sixth one states that for all natural numbers, the image of the successor function of n is inside, or is a subset of n. So any output we can get from the successor function is always a natural number. And that holds true. The successor function basically tells us if we put a number inside it, what's the number that comes after that number. And obviously, if I have 1, what comes after it, the next natural number is 2, right? So the successor function of 1 is 2. The successor function of 0 is 1. And obviously, those two are natural numbers. So this rings true, that the image of this successor function is contained entirely in n because all of its elements are natural numbers, or it should be. Right? Because we always want a notion of closeness for it to be neat and a meaningful structure. Okay. So, okay. Now, the next few axioms, 7 onto 9, will be concerning the successor function. Now, I'm gonna explicitly define it here. The successor function of a natural number n is simply equal to n plus 1. So we just add 1 to the natural number to get its successor. Okay. So the seventh axiom is that for all the natural numbers m and n, m is only equal to n if and only if their successors are the same. Okay. the eighth one is that there does not exist a successor of 0. Or there doesn't exist a natural number whose successor is 0. So you'll notice that there are no numbers below 0. There is no -1, there is no -2. This is not the integers, this is the natural numbers. We all know all natural numbers are simply positive integers, starting from 0, of course. Because you can't have -2 of something, right? Okay, so this tells us that negative numbers don't exist here. It's only positive numbers and values above 0.
Complex numbers for negative.
Yes, sir. They're not part of the
It's
naturals.
not part of that.
Yes, sir. This is just a subset of the reals, and
Real numbers. Yes.
yeah, this is part of the real numbers. It's a subset. Of.
Yes. That's why negative numbers are not part of that because it's not a natural number.
Yeah, negative numbers are not natural numbers. If we do allow that negative numbers be part, it would become the integers.
Yes.
Okay. So the last one, the last axiom concerning this is that if I have a set K such that 0 is in K and for all n inside the naturals, n is in K, it satisfies this formula, implies that its successor is in K, then K contains all the naturals. So we're basically saying that if I have some set K, such that 0 is inside it, and I have a natural number inside it, say 1 is inside it, and that natural number has a successor that's inside K, then K immediately contains all the naturals. So all of this is Peano's axioms, or the Peano axioms. Now, what about the successor function? Let's explore the successor function a little bit more before we dive into applications and how this applies to other parts of our theories. So there are a couple more ground rules that we can establish with the successor function, and once we establish that, we can prove very basic arithmetic, like say 3 plus 2 equals 5. We can prove that because we have already established our intuitive notion of addition here. I mean, not just yet, but we will soon, using the rules associated with the successor function. Okay. We also have an alternative version of 9 that's more general. It's basically just saying that if I have some formula for n, and if I have some predicate, unary predicate, which I will denote by phi, and then n satisfies phi, it must be that the successor of n satisfies phi also, if n is a natural. Okay. Okay. So formally speaking, the successor function S of n is a unary map that takes any natural number and gives us a natural number. And the reason why we call it a unary map is because it only takes in one output and gives exactly another output. And so it is explicitly defined as the image S of n equals n plus 1. It's as simple as that. It's just adding 1 to the element we put inside here. Okay. Now, a while ago I didn't quite specify exactly the formal definition of addition and the successor function in terms of the structure. So, of course, now we will do that. So, addition plus is a function that maps two numbers. It's a binary map. Here, it takes two natural numbers. So n cross n, it takes them. So we don't just say that a plus b equals some natural number c, right? We don't just say 1 plus 1 is this, 2 plus 2 is this, 3 plus 3 is this. That's not the proper way of defining this operation. The proper way of defining this function is recursively starting with 0. So, recursively speaking, addition can be defined as, okay, so it is defined recursively as, so we have two recursive definitions for the addition operator. The first one is that a plus 0 equals just a. I mean, obviously, we're establishing this. Obviously, any number added to 0 just gives that number. So a plus 0 equals a. The second one is that a plus the successor of another natural number b is equal to s of a plus b. And this one here, to be honest, is my favorite part of the Peano Axioms. Because this is the key insight or the key rule to us proving the most basic of operations, or the most basic of arithmetic, such as 1 plus 1, 2 plus 2, 3 plus 2, or 4 plus 1. It's all proven thanks to this. Okay. So, now, we know that 0, according to addition at least, 0 is our identity. But what about multiplication, right? We haven't stopped and considered multiplication in this case, because we were mostly focused on the successor function and addition. But we know intuitively that natural numbers can be multiplied. You can multiply 1 and 2 and then get 2, which is still part of the natural numbers. We can multiply 4 and 2, which get 8, which is still a natural number. I can multiply 36 by 2 to get 132, and that would still be part of naturals. It's still a natural number, albeit big, but we didn't quite explicitly state it. So this is not the correct way of saying it. So plot twist, this is not the complete structure for n. The complete structure is n equipped with addition operator, equipped with also the successor function, and lastly, the multiplication operator. So this is the real natural numbers. Okay? So right, we already defined this. We already defined addition. So keep this rule or these two rules in mind when we start proving basic operations with addition. Okay. So lastly, the multiplication operator is also a binary map. Which takes in two natural numbers and cross and gives Now, the thing with multiplication here is that we don't just consider, it is not a unified notion. There are two types of multiplication in this case here that we have to consider. Left and right multiplication. Because multiplication is not necessarily, or at least the notion of putting things together, literally, or composing them, is not necessarily commutative. Take, for example, matrices and their composition. When we compose or multiply matrices, it's not necessarily abelian, right? It's not necessarily abelian. So the group of all matrices, say the general linear group, is not necessarily abelian, but it is close nonetheless, right? But still, not abelian. Not abelian. So we have to consider left and right multiplication. So multiplying from the left, multiplying from the right, and switching the order basically. We have to consider that. Okay. So the way we define multiplication for the natural numbers is much of the same way, wherein we define or recursively define addition for the natural numbers. So for here, for multiplication, it's pretty much the same thing. Recursively is recursively defined as 1, 8 times 0 equals 0. 8 times the successor of b is equal to a plus a times b. Now, the recursive definition is not quite the same. Of course, you can see that it's different. Obviously, any natural number multiplied by 0 is just 0. How many times of something we can have, right? And since we don't want any of the object, we have 0 objects, right? So, now, this recursive definition is not so clear, but you will notice that the successor of b is just necessarily b plus 1, right? And a times that is, well, that's 1, and then we can sort of switch things around. Eventually, we would end up with a plus a times b. Okay.
Dati kasi nilalaro ko, CS ko, yung parang
So here it is. These are our important rules. When it comes to here, we are technically done defining the structure. We are done. So let's just do some exploratory things with the successor function. So first, using our definitions at hand, what the tools under our belt basically. Let's prove. So 1 and 2 are natural numbers, right? Let's prove that 1 plus 1 equals 2. Okay. So of course, you know, one object, another object together gives 2 objects, obviously. But given the definitions we have at hand, let's show that it is true. Now, we know that 1 is nothing but the successor of 0. So this becomes successor of 0 plus the successor of 0 equals 2. You know, to make it a bit more funny, let's call it the suck. So the suck. So 1 is nothing but the successor function here, the suck of 0. Okay. So the suck of 0 plus the suck of 0 gives us 2. Is equal to 2. Okay. So, or alright, sorry. we want to replace just one of these guys, okay? We just want to replace one of the ones with the successor function of 0. And we know that any natural number a plus the successor function of another number b, natural number b, gives us the successor function of a plus b. And note that our notion of addition still holds here, okay? So 1 plus the successor of 0 is nothing but the successor of 1 plus 0. And we know that a, recursively, a plus 0 equals just a, according to our definition, okay? These are definitions that I made outside of it, of what we know. Okay? Okay. So, successor of 1 plus 0, since a plus 0 is a, this just gives us nothing but suc of 1. And we explicitly, a while ago, I explicitly defined the successor function of the natural number a to be a plus 1. So therefore, the suc of 1 is equal to 1 plus 1, and that's 2. QED. Now, I can do this for an arbitrary number here. So I can basically do this inductively for any n. Okay. So what we basically do is decompose it to 0 and then stuff like that, to successors of 0 and stuff like that. This is just one proof. So yeah, it's a proof that 1 plus 1 equals 2. So application at least. Okay. Okay. Now, how does knowing about constructing the naturals apply to one of our theories, or at least some of our theories? Well, obviously, the basic notion of addition is important when we talk about position states, of course. Position theory. When we talk about position theory, addition of two states, well, at least corresponds at least, or there's some relation to it. So if we're going to use our notation from the last one, and we have our position here, let's say that P, not cal P, is our model, or at least our world for position theory. And let's say our current world of naturals is covered by N. Gold N. Now, because there is some notion or structure that is carried over from N to P, we say that these two are related. Or that, well, of course, the specific mapping of this is that so I'm gonna explicitly define the operation how it carries over to person theory, okay? So sum number A can be expressed as a sum of two numbers according to the gap. That is all mapped by R.
Like you're jumping from S to another.
So I'll say the top state, T plus P times the bottom state. So yeah, it's carried over onto this relation from this. Of course, by setting maybe some equivalence relation, or just transforming this into either a complex valued object or what. Now, of course, define this inductively. Maybe the S of dot dot the S of 0 is essentially just n, and then we of course add m to this, and then we would do some other stuff, a clever thing to get a. Alright. So just one application, or one mapping at least, or one relation between our model of the naturals and position theory. Now, how about femboid theory? How do we carry over this concept or this notion to femboid theory? Well, although we cannot exactly assign naturals to manifolds, we could do it. If I let mathcal F be the model for femboid theory, there is actually a relation, or it's a partial relation between our model N and M. And that is this over here. The relation between our femboid theory and N is precisely every manifold, some manifold, is associated with a natural number. So a natural number, or zero actually, let's use a specific one. So it's not just the entire relation between N, or the naturals, and F, but a specific one. Let's use a specific one. So 0 is taken via R to a sphere. And what exactly is R here, or our relation? Our relation is 0 is the genus of S2. So R is this relation. Then the genus of S2 is 0 because it doesn't have poles, of course. And you guys can now see what the relation is between natural numbers and femboid theory, of course. Another one, and a more general one, is basically genus itself. So I have, let's say I have a manifold, let's say I have an n-dimensional manifold, right? Or actually dimension. We have dimension, we can assign it a dimension. So n, a natural number n, can be sent by R to the n. M to the n, or n, dimensional. If it's 0, the manifold is just a point. If it's 1, it's a curve. If it's 2, it's a surface. 3, it's a tesseract-like surface. Okay, so m to the n, of course, dimension also genus, of course. So if I let m sub n be an n genus manifold, of course, n, a natural number, is taken by R to this mn via the relation. R implies that the genus of S sub n, or M. So, for example, at least 3, or 2, sorry, 2 is taken by R to the dual torus, because it has 2 poles, it's genus 2. So, there, that's another application of the naturals to our theories. Now, you may be thinking, how about relationship theory? Well, obviously, you guys can already tell by now, natural numbers are also counting numbers, right? They're essentially counting numbers. Another application is of course, in relationship theory. If I let mathcal R be our model, or our worlds, or set of worlds for relationship theory, we can now establish a relation between our model and R. And that is given by the that's given by this specific relation. That a given graph with n vertices has a population of n. Is an n or p2, right? Pn relationship. So n is taken or to a graph G or a relationship G in chart G equals n or implies that and R. So there's just one snippet of the applications of natural numbers to our theories, and why constructing the naturals is very important, of course. So let's say, for example, I have two tori in my hand, and I want to find out the total genus of the things in my space. So the space is everything around me, and I have the two tori. So let's say I want to have the total genus of the space, which contains the two tori. So that means I would have to add both of them, right? I would need to add both of their genuses, right? Or a femboid donut. I have two femboid donuts, and I want to add the genuses of those two femboid donuts. So that would entail having to use the Peano axioms to show that it is truly two. So I have two femboid donuts, and then I take the genus of one, I take the genus of the other. I get one here, then one the other. When I add both of them according to the Peano axioms, which is true, it is two, genus two in total. So yeah, or if you consider a two-fold femboid donut, piece by piece, with respect to the genus or with respect to the wholes, we would have to use the Peano axioms to show that the addition of the genuses of these constituent parts really equal to. So yeah. So that's our application of the natural numbers and their operations to everything. So, any question? Kyle. Kyle. Got a question? None? Why is it the big oh, right. You don't want to get it? I have lectures. It's more of B though. Huh? I think it's more of to put it simply, we just have we assign a point to a femboid. So I have a femboid, and then I label it using a point, basically. So he's represented by a point, and then we have a bunch of those points that form the shape of a donut. That's a femboid donut. Yep, I guess it's an abstraction, basically. We abstract them, and then yeah, it's best discussed in femboid theory. So you can just check the playlist on that. The specific one, femboid donuts. Right. But it's a bit abstract, so I'll just say that it's I have one circle. I have a circle. I have S1, and then I have another circle, and then I make the circle in between. I interlink them like this, and then I make it go around, or make copies of that circle all around, and you notice it becomes a torus right there. So that's just one application. So I think the next one, we're a bit out of time. So the next one, we're just going to be talking about the real numbers, actually construct the real numbers. And I know it's going to be a bit hard, and we will run into stuff like omega in the future, where its infinity is bigger than the infinity we know. A value that gets arbitrarily large. There's something bigger than that. If we treat infinity as an object, which we really should, in set theory at least, or in this course, we notice that there are objects bigger than it, especially when we talk about the well-ordering principle. So that's it for this lecture, and that's a good place to stop.